Good day and welcome to One-on-One Maths Private Tutors. Today we look at O-Level and IGCSE Physics for Pure Physics and Combined Science. The topic is practical electricity. Uses of electricity. The first use of electricity is electric lighting. Let's look at LED lights. LEDs, or light-emitting diode lights, are increasingly being used in lighting of our homes. These semiconductor devices are 40 to 50% efficient in transferring the energy carried by an electrical current to light. The efficiency of the filament lamps used in the past was only about 10%. So LEDs save electrical energy, therefore saves money because of their efficiency, which is high. Fluorescent lamps. Fluorescent strip lamps are long-lasting and efficient. When one is switched on, the mercury vapor emits invisible ultraviolet radiation, which makes the powder on the inside of the tube fluoresce or glow. Therefore, visible light is emitted. Different powders give different colors. Compact and energy-saving fluorescent lamps, which are these ones, are commonly used in home lighting. So this is a picture of fluorescent strip lamps, and these are compact energy-saving fluorescent lamps. Electricity is also used for heating in heating elements. In domestic appliances such as electric fires, which we normally call heaters, cookers, electric kettles, and irons, the heating elements are made from nichrome wire. This is an alloy or a mixture of nickel and chromium metal, which does not oxidize or react with air when current moves through it. So when electricity passes through them, they become red hot and do not react with air. The elements in radiant electric fires are at red heat at about 900 degrees Celsius, and the radiation they emit is directed into the room by polished reflectors. In convector types, the element is below red heat at about 450 degrees and is designed to warm the air, which is drawn through the heater by natural or forced convection. In storage heaters, the elements heat fire clay bricks during the night by using off-peak electricity. On the following day, these cool down, giving off the stored heat to warm the room. So this is an example of a radiant electrical fire. This is an example of an electric cooker. And this shows the element of an electric kettle. And this is the element of an electric iron. Electricity is also used to charge batteries. A battery charger transfers energy to a secondary cell or rechargeable battery by forcing an electric current to flow in the opposite direction to the normal current flow from the cell. Some rechargeable batteries, such as those used for the electric car, require a fast rate of charging. Others, such as batteries used for electric lawnmowers or mobile phones, use a slower rate of charging. A battery charger should be switched off after charging batteries that can be damaged by overcharging. The life of a battery can be prolonged if the correct charging method is used, as well as mains-operated battery chargers. The PD from solar cells can be used directly to charge a battery. So we can charge a battery from the plug or from solar cells. A smart battery charger can adjust its rate of charging according to the state of the charge of the battery. So it will have sensors to know when to slow down the charging or to increase the charging. This is useful for making cost-effective use of energy supplies, for example, from a rooftop solar system. Electricity can also be used to power motors. A motor is a device that converts electrical energy to mechanical or kinetic energy. Electric motors are found in many electrical appliances, from sewing machines, vacuum cleaners, electric cars, and trains. So anything that has movement will require a motor to convert the electrical energy to kinetic energy. An electric motor transfers the energy carried by an electric current to kinetic energy. The power required by a motor is given by the equation P is equal to VI, where V is the voltage and I is the current. The unit for power is the watt. The power needed for the motor in an electric car is around 100 kilowatt or 100,000 watts. For a DVD player, only about 20 watts are required. The power required depends on the work done by the device. Electricity can also be used in electronic systems. Electronics are used in our homes, factories, offices, banks, and hospitals. The development of semiconductor devices, such as integrated circuits, has given us things like computers, programmable control devices, robots, home entertainment systems, digital cameras, and heart pacemakers. Electric circuits enable electrical signals to be processed. An electronic system can be considered to consist of three main parts: an input sensor, a processor, and a device called an output transducer. Input sensors detect changes in the environment and transfer energy from its present form to an electric current equivalent. Input sensors include LDRs, or light-dependent resistors, thermistors, and also microphones and pressure switches. The processor decides on what action to perform on the electrical signal it receives from the input sensor. It may involve operations such as counting, amplifying, timing, or storing. The output device transfers the energy carried by the electric current in the processor to the environment. These devices include lamps, LEDs, loudspeakers, motors, heaters, relays, and oscilloscopes. In a radio, the input sensor is the area that sends an electric signal to the processor in the radio. One of the functions of the processor is to amplify the signal so that a loudspeaker can produce a sound wave. Electrical energy is converted to other forms of energy in an electrical device. For lighting, electrical energy is converted to light energy. In heaters, electrical energy is converted to heat energy. In battery chargers, electrical energy is converted to chemical energy. In motors, electrical energy is converted to kinetic energy. From our definition, potential difference is the work done in moving a unit charge between 2 points. So, V, which is our potential difference, is work done per unit charge. We can rearrange this equation to have work done as the product of the potential difference and the charge. But power is work done over the time taken, or the rate of doing work. So power can be calculated also as VQ over T. But Q over T, the rate of flow of charge, is current. So power is equal to V times charge over time from this equation. And we can substitute charge over time with current. So power is equal to voltage times current. So this is a very important equation. The unit of power is watts. The more commonly used multiple is the kilowatt. 1 kilowatt is equal to 1000 watts. Let's look at this question. A stove uses 12,000 joules of energy in 10 seconds. Calculate the power it consumes in this time. So power is the rate of doing work, which is work over time. Work is the energy converted. So we can say energy over time, which is 12,000 over 10, which will give us 1,200 watts. Now, power is equal to voltage times current, and current is equal to power over voltage, which will give us 1,200 for our power over the voltage, which is 240. This will give us 5 amps. So that's how much current is flowing through it. Power is the rate of doing work or the rate of conversion of energy. So in electricity, electrical power is electrical energy over the time. And energy is power times time. Power is equal to voltage times current. So electrical energy is calculated as voltage times current times time. Now we want to introduce the kilowatt hour. 1 kilowatt is 1000 watts. We can write power supplied to a device as energy consumed per unit time. And energy is equal to power times time. If power is measured in watts and time is measured in seconds, so we can say the unit of energy is watts seconds. To convert power to kilowatts, we can divide the watts by 1000, and to convert the seconds to hours, we can divide by 3600. Dividing by 1000 will give us kilowatts. Dividing seconds by 3600 will give us hours. So the kilowatt hour is another unit for energy. The watt second is equal to the joule. 1 kilowatt hour is equal to 1000 watts, converting 1 kilowatt to watts, and the hour is 3600 seconds, which will give us 3.6 times 10 to the power 6 joules. So to convert from kilowatt hours to joules, we multiply by 3,600,000, which is 3.6 times 10 to the power 6. And to convert from joules to kilowatt hours, we divide by 3,600,000. So kilowatt hours and joules are both units of energy, where the joule is equal to the watt second. The kilowatt hour is the commercial unit used to measure the electrical energy supplied or consumed in households and industry. Now, another equation we should know comes from this equation. Energy is equal to power times time, but power is equal to VI. Therefore, electrical energy is equal to voltage times current times time. This is another important equation. So the two primary equations we are supposed to know are this equation and this equation. Let's look at this question. For the circuit shown, the potential difference across the bulb is 12 volts. So we have 12 volts on this bulb. The current through the light bulb is 3.2 amps. So to calculate the power, say power is equal to VI, which is 12 times 3.2, which will give us 38.4 watts. Now, to convert it to kilowatts, we divide by 1000. So this is 38.4 over 1000, which will give us 0.0384 kilowatts. The light bulb is kept on for 2 hours. Calculate the electrical energy the light bulb used in this time. From E is equal to power times time, you can say electrical energy used is 0.0384 times 2. So this is kilowatt and this is hours. This will give us 0.0768 kilowatt hours. Let's look at this example. A lamp rated 6 volts, 2 amps is switched on for 60 seconds. How much energy is used? So we can say energy is equal to power times time, which is power is VI, voltage times current, times time, which is 6 times 2 times 60, which will give us 720 joules. Let's look at this question. Which quantity is measured in kilowatt hours? Quantity measured in kilowatt hours is energy. So electrical energy can be measured in kilowatt hours or joules or watt second. A battery is used to light a 24-watt electric lamp. The battery provides a charge of 120 coulomb in 60 seconds. What is the potential difference across the lamp? From this information, we can find the current. Current is the rate of flow of charge over time, which is 120 over 60, which will give us 2 amps. Power is equal to voltage times current. Making voltage the subject of the formula, we say V is equal to power over current, which is 24 over 2, which will give us 12 volts. So our answer is B, 12 volts. Let's look at this question. The diagram shows the circuit of a hair dryer. We have a fan, heater. The fan has a power rating of 0.1 kilowatt and the heaters each have a rating of 0.4 kilowatt. What is the cost of running the dryer for 2 hours with switches P and Q closed and switch R open? So we are closing this P and Q. The total power will be 0.4 plus 0.1, which is 0.5 kilowatt. Energy is equal to power times time. Our power is 0.5 times our time is 2 hours, which will give us 1 kilowatt hour. So our energy is 1 kilowatt hour. The cost is 8 cents per kilowatt hour. So cost is energy consumed, which is 1 kilowatt hour, times the cost per kilowatt hour, which is 8 cents. So our cost will be 8 cents. So our answer is D. So that is how electricity is costed. Once we find the rate for a kilowatt hour, we calculate the energy that is used first, then we multiply it by the cost per kilowatt hour. A small heater operates at 12 volts, 2 amps. How much energy will it use when it runs for 5 minutes? Power is equal to voltage times current, which is 12 times 2, which is 24 watts. Energy is equal to power times time, but our time needs to be converted to seconds. Time is equal to 5 times 60, which is 300 seconds. So our energy will be 24 times 300, which will give us 7,200 joules. Now, if we were asked for our energy in kilowatt hours, we would take this 24 watts is equal to 24 over 1,000, which is 0.024 kilowatts. Then 5 minutes is equal to 5 over 60, to convert it to hours, which is 0.083 hours. Now, to make it kilowatt hours, we would multiply these two. 0.24 kilowatts times 0.083 hours, which is 2 times 10 to the power minus 3 kilowatt hours, or 0.002 kilowatt hours. Another way to convert from joules to kilowatt hours is to divide 7,200 by 3,600,000, or 3.6 times 10 to the power 6, which will also give us 2 times 10 to the power minus 3, or 0.002 kilowatt hours. So we can see how we convert between the two units, joules and kilowatt hours. Thank you.